Yeah, the next 20 minutes will be about breaking elliptic curve keys on a quantum computer. And the talk is based on two papers. The one on the left with Naomi Nickerson about an architecture for fault tolerant quantum computing that takes advantage of the long range connections that you have available with photonics. And a second paper on the right about elliptic curve cryptography. And because this is the cryptography session, we will primarily focus on the second paper. Now, there are two things that you can expect to see in this talk. We'll first look at how to perform a resource estimate for breaking 256-bit elliptic curve keys on a fault-tolerant quantum computer. And towards the end, I'll show you a few simple algorithmic tricks that can reduce the Toffoli count for breaking elliptic curve keys by up to a factor of 5. Let's first talk about resource estimates. Now, the goal of a resource estimate is to determine how long, how many minutes, hours, or days it takes to finish a quantum computation, and how big a fault-tolerant quantum computer needs to be to run it. And I would say the main interest in performing a resource estimate for a cryptography algorithm is twofold. On the one hand, it lets us quantify the cryptographic implications of fault-tolerant quantum computers, because when the first quantum computers appear that are just large enough to break relevant key sizes, it makes a difference if it takes 10 minutes to break a key or 10 years. On the other hand, they are great benchmark algorithms. So, with resource estimates for quantum simulation algorithms, there can be a lot of ambiguity about the inputs and outputs of the problem. On the other hand, breaking keys is a very well defined mathematical problem with clear inputs and outputs. And resource estimates for cryptography applications often set the bar for other applications to determine if a computation is cheap or expensive. Now, for a resource estimate, it's important to know what the quantum computer looks like, so what architecture it uses. And we'll look at how to perform a resource estimate for two different fault tolerant surface code architectures. They are both general purpose architectures that make it easy to perform a resource estimate, even if you know nothing about quantum error correction. The, the first architecture on the top is a standard architecture based on 2D local connectivity. And the second architecture is the active volume architecture that relies on long range connections between logical qubits. And these are motivated by silicon photonics and can significantly speed up quantum computations. So, first, a brief overview. A 2D local baseline architecture consists of n logical qubits, where roughly half are used as memory and the other half as workspace to execute logical operations. Each logical qubit here is drawn as a square, but really corresponds to potentially thousands of physical qubits. A few logical qubits are reserved for magic state distillation, but this is typically only a small fraction. A baseline architecture executes gates entirely sequentially, one gate after the other. So if you have n logical qubits, then you have n half logical qubits of memory. So you can execute quantum computations that require this many qubits. But the speed is always 1 T gate per logical cycle, or 1 Toffoli gate every 4 logical cycles. And here the length of a logical cycle can range from a few dozen microseconds for superconducting qubits to a few dozen milliseconds for ion traps. That is to say, all you need to know is the qubit count and Toffoli count of an algorithm, and then you can also compute how many minutes, hours, or days it takes to finish the quantum computation. Now, in an active volume architecture, the picture is a bit different. We still have half the qubits used for memory and half as workspace, although now distillation is also done in the workspace. But rather than executing operations sequentially, we use the long range connections to parallelize operations. To quantify how many operations we can execute in parallel, we say that with n half workspace qubits, we can execute n half logical blocks per logical cycle. So different operations have different costs, and the number of logical blocks is a measure of how costly an operation is. So logical blocks are basically the currency that we pay for logical operations. For example, the cost of a Toffoli gate in an adder is roughly 60 blocks. The workspace is used to execute as many operations in parallel as possible, and the primary purpose of these long-range connections between logical qubits is to quickly rearrange the memory between logical cycles, because different operations access different qubits that are stored in different memory locations. So the main difference between the baseline and active volume architecture is that whenever we add logical qubits to an active volume quantum computer, we increase the memory and we also increase the speed, whereas in a baseline architecture, the speed remains constant. Now, if we think of our algorithms not in terms of small gates like Hadamard's and Toffolis, but instead in terms of bigger subroutines like adders, comparators, and table lookups, then the steps to perform resource estimates are very similar for both architectures. We just count the different subroutines and then assign a cost to each subroutine using this table in the bottom left corner. For the baseline architecture, it's the Toffoli count, and for the active volume architecture, it's the active volume. There can be some differences because the ratio between active volume and Toffoli count differs from subroutine to subroutine. Generally speaking, arithmetic subroutines like adders and comparators have a very favorable ratio of roughly 60 blocks per Toffoli gate. On the other hand, lookup tables can be much more costly in terms of active volume, since their active volume scales with the size of the bit strings that are loaded into the quantum computer, whereas the Toffoli count is not. Now, let's perform a resource estimate for Shor's algorithm for breaking elliptic curve keys on a quantum computer. So next to RSA, elliptic curve cryptography is one of the two widely used public key cryptography schemes, and it has been known for a long time that both RSA and elliptic curve keys can be broken efficiently by quantum computers using Shor's algorithm. And it has also been known that since commonly used elliptic curve key sizes are smaller than RSA keys, it is cheaper to break relevant elliptic curve keys than RSA keys. So recommended elliptic curve key lengths are 256 bits, whereas in RSA, typically people use 2048-bit or even 4096-bit keys. The smaller keys are seen as an advantage of elliptic curve cryptography because they provide you with the same level of security but allow you to work with smaller numbers. But for a quantum computer, the fact that one requires 256-qubit arithmetic and the other one 2048-qubit arithmetic makes a big difference, making elliptic curve keys easier to break. There are several curves that are used for cryptography, but our guiding example will be the widely used and NIST recommended elliptic curve that goes by the name SECP256K1. Let me first summarize how elliptic curve cryptography works in the first place. If you're not familiar with elliptic curves, it's best to, not to worry about the word curve at all and just consider the following operational definition. An elliptic curve point is a pair of 256-bit numbers, at least for 256-bit keys. There's an operation called elliptic curve point addition. If you have 2 points P1 and P2 specified by coordinates x, y, and a, b, the addition operation allows you to compute the resulting point P1 plus P2. But this is not a simple addition. You compute the coordinates of this point by performing a bunch of modular arithmetic operations modulo p, where p is a prime number, at least for most relevant curves. For our guiding example, it is this 256-bit number p shown below. For the point addition prescription, you need to multiply some numbers, add some numbers, divide some numbers, but all operations here are modular operations mod p. Actually, I'm simplifying a little bit here because there are some exceptional cases in elliptic curve point addition. So when the 2 points are equal or opposite of one another, or if one of the points is the so-called point at infinity, which you can also think of as a 0 point, there's a slightly different prescription. But let's not worry about this here. You can also define something called elliptic curve point multiplication. The point k times p is just the sum of kp points. And it is easy to compute any point k times p from k and p because you can do repeated doublings to obtain the points 2p, 4p, 8p, 16p, and so on, and then add them up in the right quantities. But the opposite operation is actually quite hard, or at least there is no known classical algorithm to do this efficiently. Given a point p and a point q that is a k multiple of p, it is difficult to compute k. And this is what's used in elliptic curve cryptography. There is a base point p known to all participants. For example, at the bottom, you see the x-coordinate of the base point used for this specific curve. And if you want to generate a private key and a public key, you generate a random 256-bit number k and compute q equals k times p as the public key that you announce. Since other people only know the public key q and the base point p, they will have a hard time determining k, the private key. Now, on a quantum computer, you can run Shor's algorithm to compute the private key, knowing only the public key and the base point p. And here's the quantum circuit of the algorithm. The circuit consists of 2 phase estimation steps. The first step is a phase estimation using the unitary UP that acts on 2 256-qubit registers, storing an elliptic curve point, and performs an elliptic curve point addition with a point p in superposition. So the unitary UP is the one that acts on 2 registers storing the point r, and transforms it into r plus p. So r and p are elliptic curve points here. The second phase estimation step does the same, but adding q instead of p, so the public key instead of the base point. A phase estimation is something that generates an eigenstate of the unitary u and outputs the corresponding eigenphase. So in this case, the first phase estimation generates a superposition of states psi c entangled with c, where psi c are eigenstates of up and c is the corresponding eigenphase. There's an important known property of the base point, and it's called the order r of the base point. So if you add p r times, you get the point at infinity. Or in other words, if you add it r plus 1 times, you get back to p, where r is this 256-bit number for our example curve shown at the bottom. We can use this to understand what all the eigenstates of up look like that overlap with the base point p, because they're all just equal superpositions of all multiples of p, and only differ by how quickly the phase winds as you go through the superposition. So there's, for example, the eigenstate psi0, which is 0p plus 1p plus 2p plus 3p and so on. Or the state psi1, which is the same superposition, but there's an increasing phase in front of every superposition term. So here we have a phase phi r, 2 phi r, 3 phi r, and so on, where phi r is 2 pi over r. Psi2 is the same, but the phase increases in steps of 2 phi r. And so all eigenstates of psi c with an eigenphase, all eigenstates of this unitary are psi c with an eigenphase that is c times 2 pi over r. When we measure the control register of the phase estimation, we then effectively obtain a random number c and project the remaining qubits onto the corresponding eigenstate psi c. One important thing to note is that the state psi c is not only an eigenstate of up with an eigenphase that is c times 2 pi over r, it is also an eigenstate of uq, but rather than having an eigenphase c times 2 pi over r, it has an eigenphase that is c times k times 2 pi over r, so the private key multiplied by this number c. If we perform the second phase estimation with uq, we can then directly obtain c times k as the output, and dividing this number c times k by c allows us to retrieve the private key. So to summarize, Shor's algorithm for breaking elliptic curve keys can be thought of as consisting of two steps. First, we perform a phase estimation with the unitary up that performs elliptic curve point addition with the base point p, and this generates a random number c and a random state psi c. And then we perform a second phase estimation on this resulting state with the unitary uq that uses the public key q, and we obtain the rescaled private key c times k. Dividing c times k by c gives us the private key k. Now let's perform a resource estimate for a baseline architecture and for an active volume architecture. In the first case, we need to count the total number of Toffoli gates, and in the second case, the total active volume. The only thing that we use to assign costs to subroutines is this table, which is derived from estimates that are found in the active volume paper. The table contains only a few basic subroutines, but the quick summary is that n-qubit adders and similar circuits like subtractors and comparators cost n Toffoli gates, or 60 n blocks of active volume. And the table also contains QROM lookups, which are the quantum version of lookup tables. Importantly, it has nothing to do with QRAM. Loading such a lookup table with k entries costs k Toffoli gates, but the active volume also scales with b, the size of the loaded bit strings. Uncomputing a lookup table can be done with cheaper operations as described in the literature. Now, if we want to use this table for our resource estimate, then the first step is to take this algorithm and break it down into these basic subroutines. We will first do things very similarly to the way that they are described in the existing literature in these papers, and then we will add a few simple improvements on top. Rather than implementing each of these controlled elliptic curve point additions with a separate point addition operation, the literature tells us to use a trick called windowing to reduce the number of point addition operations we need to perform. This takes advantage of the fact that we can use a lookup table to load some pre-computed points into the computation. So we replace each group of 16 controlled unitaries with a 2 to the 16 item lookup table and a single elliptic curve point addition, easy point add. And this we repeat 16 times for the first phase estimation and 16 times for the second. So rather than overall performing 512 controlled elliptic curve point additions, we only have 32 QROM lookups and 32 EC point add operations for the entire computation. And therefore the main question is, how costly is an EC point add? The EC point add operation takes 2 points, a, b, and x, y as inputs, so that's our points p1 and p2, and computes their sum, x, r, y, r, using this prescription that I showed you before. For this, it uses 6 additional 256 qubit ancilla registers, and we break down this operation into more elementary operations, specifically into modular arithmetic operations. Just to convince you that there's no magic happening here, let me just show you the circuit. If you want to understand the circuit in detail, it's explained in the paper, but don't try to understand it now. It is really just a sequence of reversible arithmetic operations known from the literature that implements elliptic curve point addition. And the operations that we find here in the circuit, they are modular additions, modular subtractions, negations, doublings, multiplications, and computations of the inverse, 1 over x. For the resource estimate, we just count these operations, and we find that each EC point add consists of this many modular arithmetic operations as shown in the bottom right table. And because none of these modular arithmetic operations are in this left table of basic subroutines, the next step is to decompose these modular arithmetic subroutines into non-modular arithmetic so that we can obtain Toffoli counts and active volume estimates. Again, we use prescriptions that are known from the literature. I will just flash a very brief overview. For example, modular addition can be done with 3 non-modular additions in a comparator, which is 4n Toffolis or 240 n blocks of active volume. Negation, subtraction, and doubling can also be done with standard non-modular arithmetic, and that's how we arrive at these numbers. N-qubit multiplication based on Montgomery multiplication can be done using n over 4 repetitions of this operation that contains a few adders and a lookup table. The important thing to note here is that multiplication is much more expensive than the previous operations because it scales with n squared. But what's even more expensive is inversion. The best circuits for computing the modular multiplicative inverse that are described in the literature are found in these 3 papers. They're based on an optimized classical algorithm called Litinski's algorithm, which computes the modular inverse using up to 2n rounds of reversible operations. This results in a cost per inversion that is over 10 times the cost of a multiplication. And since we have 4 of those inversions in each EC point add, it's really the dominant cost contribution. Now, in principle, we're ready to perform a final estimate, but in addition to what's described in the literature, we'll make a few simple adjustments to the algorithm that can improve the resource count by up to a factor of 5. The first adjustment is based on the observation that the first half of the algorithm is just a preparatory step that sets up the quantum computer to compute the private key in the second step. But if we want to compute multiple private keys of the same elliptic curve, which is the typical situation since almost all keys use the same elliptic curve, we don't need to repeat the first step. The state that we generate in the first step is a simultaneous eigenstate of all UQs of all public keys of that elliptic curve. So we can asymptotically halve the cost by only repeating the second step for each key that we generate. So what this circuit right here says is that when we're recovering multiple private keys, K1, K2, K3, and so on, with public keys Q1, Q2, Q3, and so on, then we only do one phase estimation with the base point to obtain this random number C, and the next phase estimation with Q1 gives us the rescaled private key C times K1. The next phase estimation with Q2 gives us C times K2, and so on. So asymptotically, we only need one phase estimation per private key, not 2 as in the original description. The second adjustment is that rather than executing 16 of those group of 16 operations, we'll only be executing 13 of those. Now, this gives us a relatively mild cost reduction of around 20%. So effectively, we'll use the phase estimation to only compute 208 of the 256 bits of the private key, and the remaining 48 bits can be brute forced on a classical computer. So a single CPU can check over 100,000 keys per second. So even though 2 to the 48 keys sounds like a lot, you can go through them in less than 1 million CPU hours. And with costs per CPU hour of a few cents, that's definitely worth doing. In fact, I was notified after the archive publication that something similar was also suggested by Martin Eckera in one of his papers, although the fault-tolerant resource estimates in the literature didn't take advantage of that. The third adjustment is that we can spread the cost of the expensive modular inversion operation over multiple parallel instances of the algorithm. The dominant cost of the quantum algorithm lies in the modular inversion, so computing 1 over x from x. There is a known classical computing trick that if you want to compute 2 inverses of 2 numbers x1 and x2, you can do that with a single inversion by first multiplying the 2 numbers, computing the inverse of the product, 1 over x1 times x2, and then getting 1 over x1 by multiplying with x2 and 1 over x2 by multiplying with x1. And you can use the same trick in a quantum circuit, and it also generalizes to more numbers. So asymptotically, you use just 3 multiplications per number to compute an inverse, which can reduce the cost per inversion by up to a factor of 4. But in our algorithm, we're never really inverting multiple numbers in parallel. The way you can make use of this is to run multiple instances of the elliptic curve algorithm in parallel, generating multiple keys in parallel. Each instance of the algorithm uses roughly 3,000 logical qubits of memory. Now, let's say, for example, that you have 6,000 logical qubits and you're running 2 instances of this algorithm in parallel. You can execute logical operations in an alternating fashion. First one operation of the first instance and then an operation of the second. Eventually, both instances will arrive at the point when they both need to compute an inverse. They can then make use of the cheaper modular inverse operations to replace these 2 inversions with 3 multiplications and a single inversion. And the more instances you run in parallel, the larger the cost reduction per instance using this trick. In other words, the more qubits we use, the fewer Toffoli gates we need per key. Putting everything together, we obtain the following resource estimate. Each instance of the algorithm uses around 3,000 logical qubits. Running one instance in parallel, running only one instance, the cost per key is around 110 million Toffoli gates. If we use 6,000 logical memory qubits to run 2 instances in parallel, we effectively reduced the cost per instance from 110 million Toffolis to just around 75 million Toffoli gates per key. And the more memory we use, the cheaper it gets, down to a limit of 44 million Toffoli gates per key. And the same applies to the active volume. You might be wondering, 50 million Toffoli gates, is that a small number? Is it a big number? It is indeed a small number. So for comparison, RSA 2048 requires over a billion Toffoli gates, and the smallest known commercially relevant FOMOCO-sized quantum simulations are around 10 billion Toffoli gates. Even the smallest known classically intractable simulations, regardless of commercial relevance, are around a few million Toffoli gates. Qubit count, number of Toffoli gates, and active volume are all that you need to determine concrete runtimes, as described in the paper. Now, this table contains resource estimates for trapped ion superconducting qubits and photonic qubits, as well as architectures with and without long-range connections, and you can inspect it more closely in the paper. I will just quickly highlight a few data points. Using an architecture without long-range connections, so a 2D array of physical qubits, it takes 3.8 hours to break a key using 9 million physical qubits with a 1 microsecond code cycle, as with superconducting qubits. With a 1 millisecond code cycle, as we can expect with trapped ions, the time increases to 160 days per key. The addition of long-range connections lets the quantum computer break keys over 200 times faster. And the only platform for which we have a concrete proposal for how to implement the specific switchable long-range connections required by the active volume architecture is silicon photonics. And here we find that with a 10 microsecond code cycle, a 6,000 logical qubit device can break a key every 10 minutes. A photonic quantum computer is not an array of physical qubits, but instead a network of photonic resource state generators, so the footprint is measured a bit differently, but this is also explained in the paper in more detail. If we use a 4 times bigger quantum computer, we can break 4 keys in parallel, but using the cheaper parallel modular inverse, we reduce the time per key by a factor of 7, reducing the overall cost per key. If you would like to read more about the fault tolerance aspects of the active volume architecture, you can read the active volume paper. But if you just want to learn how to perform resource estimates using the elliptic curve cryptography algorithm as a case study, you can read the second paper, both of which you can find on the archive. And with that, I hope we have a few more minutes for questions.
You can just come up to the mic.
I'm sorry, I haven't read the active volume paper yet, but do you have an intuitive explanation for what one quantum of active volume is? Like what is one active volume in this count that you're showing here?
Well, so we usually count, when we count the cost of surface code quantum computations, we usually consider the space-time volume. So the logical qubits multiplied by the number of logical time steps that we need to execute. When we do this with just local connectivity, often if we consider sort of how much space-time volume do we generate to execute a quantum computation, we find that a lot of the space-time volume that we generate is used for operations that do not contribute to advancing the quantum computation. So we have a lot of idling qubits, or we have a lot of qubits that are used to establish connections between qubits that are far away. With active volume, we refer to the volume that is really intrinsically there to advance the quantum computation. And we can use sort of an architecture with long-range connections to execute quantum computations in a way where we avoid generating this redundant volume as much as possible. And so we refer to active volume as sort of the volume that is required in a quantum computation.
This is units of 1 qubit wide by 1 qubit, 1 qubit in all directions by 1 qubit of time.
Yeah, so usually it would be like a d cubed volume, so d by d by d.
Units.
Yeah, 1 logical qubit times 1 logical cycle, which is d code cycles, where d is the code distance.
Go ahead.
Cool. Thanks for the talk. So I find this division being very expensive to be a bit amusing. Do you think there's room for improving algorithms for doing that division, or like finding it approximately the same way? I'm thinking like analogously to like the inverse square root trick, like famously used by Quake to compute that fast.
Yeah. So with the division, people have actually, there was sort of these several papers that have really put a lot of effort into reducing the cost of these three, into reducing the cost of this operation. The algorithm is basically, it's based on sort of finding the greatest common divisor. And there might be, I myself have not put any effort into reducing the cost of this subroutine, so there might be sort of some gains. Yeah, having said that, sort of maybe there's something to look into sort of for specific P's, whether, if you know what the prime number is with respect to which you're doing the modular inversion. Maybe there's sort of a way to exploit that to make it cheaper. But I have not myself attempted that.
Thank you.
Okay. There's no additional questions. Let's thank the speaker again.